To measure neck flexion extension, a reference Trignovanti IMU was placed at previously calculated centroid, while a second IMU was positioned near the fourth cervical vertebra or C4. Using these IMUs, angular motion was obtained and represented as angle versus time curves. The reference curve was taken from the paper Relationship between Neck Kinematics and Neck Disability Index, an approach based on functional regression. The aesthetic figure presents cervical angle and angular velocity curves during the flexion extension movement. The gray lines correspond to individual curves, the black line represents the mean, and the dashed line indicates plus and minus 1 standard deviation. Angles are measured related to neutral position, with positive and negative values indicate opposite directions. The curves using normalized time and shows a peak amplitude close to 15 degrees.
Alright guys, in here we have the code that we use for interpreting the raw data from the EMUs. And first in here we have the libraries that we use with every description and the math constant and the class quaternion. This class had a constructor and 4 functions that are the conjugate, the normal square, the inverse, and the multiply. And we have to understand that this sensor, this EMU, this inertial measurement unit, provide us a 4-dimensional vector that are complicated for a human to interpret. So we decided to convert it into Euler angles that are much easier to understand. And before apply it, we have to use a filter because this sensor takes a lot of electrical noise from the ambient. So we made it with the Butterworth filter using a sample and a cutoff frequency in the set coefficient. And after that, we use the class Euler angles to convert this filter data into movement angles to the neck, that are the jaw, the pitch, and the roll.
Hi teacher, I'm going to explain data processing, normalization, and zero remove. First, zero removal. Some sensor reading contain zero quaternions, which indicate measure errors. During data loading, any rows where W, X, Y, or Z is automatically removed to avoid problems in later processing. Next, normalization in static calibration. Normalization corrects the static bias of the sensor. We compute the average quaternion from static calibration data and its inverse. Then, each ground quaternion is multiplied by this inverse to obtain a calibrated quaternion and remove mountain errors. And finally, processing and filtering. We load a dynamic data and remove invalid zeros. Next, we compute the static inverse one. After that, each sample is calibrated. And finally, sent to Waterworth filters so only by it and correct data is processing. Thank you.
Here we have our code. Yeah, this code we compute this code and we obtain the value for R. And this value will be 0.9073. What does this indicate? Well, this indicates a strong positive correlation between the experimental data and the reference curve. These results suggest that both signals have a very similar temporal behavior, despite experimental noise and measured variability. You may notice that the full MATLAB code is not shown in this presentation. This is because the goal is to explain how the correlation coefficient was obtained, not to detail every programming step. Therefore, only the key parts of the code relate to interpolation and correlation calculation are shown, while the remaining steps are data preparation and do not affect the value of R.
Result analysis kinematics correlation. Data processing and normalization. Data selection. Average data from sensor. EMU1 and EMU2 were selected to capture the peak momentum. References comparison. The experimental data is compared against this discrete functional mean curve from the reference paper. Normalizations 0, 1. Amplitude to both signals to evaluate morphology beyond absolute amplitude. Aliens, the experimental inflection plays with the literature's positive tendency. Static evaluation, visualize figure one's kinematic comparison normalize. Visual analysis, the experimental curves blue match the references red in ascendance and descent place showing the characters bell-shaped. Correlations coefficients are R equal 0.19. These high values validates that the emus prototype finally falls reproduces the kinematic dynamic